Okay, welcome everyone to the Zoom Algebraic Geometry Seminar. We're fortunate to have this week Alan Thompson speaking on mirror symmetry for fibrations and degenerations.
Okay, so hi everybody, thanks for the intro, thank you for the invite. So as Chuck said, I'm going to talk about mirror symmetry for fibrations and degenerations. I'm using my homemade visualizer over here, so I'm going to spend a lot of this talk looking not directly at the camera, because if I put the camera in front, it gets blocked by the things. So anyway, I was hoping this talk would be a bit more, I was hoping to have more to report. So this talk is going to be a lot more philosophical than I hoped it was going to be. There is a theorem coming at the end, but the theorem is not as powerful as I was hoping it was going to be when I agreed to do this a few months ago. This is largely the fault of a lot of teaching related uncertainty that's required. I spend a lot more time on teaching prep this year than I originally expected to do. Anyway, there's going to be a bunch of philosophy at the start, and we'll get through to some more concrete stuff at the end. So let's start off with some philosophy. So, I mean, the first person to kind of talk about these or think about these questions, I think, was Turin in a paper that appeared, well, it got published in 2004. And it's, you know, there's just a sort of sentence at the end of the paper which talks about splitting up, you know, degenerating Calabi-Yaos, and there being some mirror towards this in terms of fibrations. And in joint work with Chuck Duran, who this is also joint with, Andrew Harder and me, which came out in, well, appeared in print in 2017, we investigated this a little bit further. So I'll sort of give you the overall philosophy to start off with, both as a way of introducing and also as a way of setting up some notation. So what I'm going to do is I'm going to look at a degeneration of Calabi-Yau to a pair of quasi-Farnos. What do I mean by quasi-Farno? This is sort of a slightly non-standard term. What do I mean? I mean, so, you know, we all know that Farno is K of X is ample, weak Farno is K of X is nef and big. Sorry, minus K of X, anti-canonical. I want to go even weaker than this. Basically, I just want to assume that minus K of X contains a smooth Calabi-Yau member. And there's going to be a condition on vanishing on cohomology. HIXOX is 0 for I greater than 0. So that's what I mean by quasi-Farno. It's quite a weak condition. Basically, I'm thinking about, well, I'll draw the picture. So here I've got some sort of Calabi-Yau thing. I'll call this V. And I'm thinking about taking this and degenerating it. And what I want to do is I'm going to degenerate it, and I'm thinking just purely at first about a degeneration. Sorry. Sorry about that. So I'm thinking purely about a degeneration where I'm taking this thing and I'm breaking it in half. And if we think about what this has got to do, you know, my V is a Calabi-Yau. When I do such a degeneration, I've got to have a situation where it breaks into two pieces. These two pieces are, I'm going to impose that they meet along a smooth divisor. And, you know, by Calabi-Yau degenerations, this thing has got to be, both of these things have got to be quasi-Farno. So we'll call this a Turin degeneration. It's a type of type 2 degeneration. Oh, I shouldn't write over there. It's a little bit blurred. The camera fuzzes out towards the edges. So if I introduce a bit of notation here, am I still on the screen? I am still on the screen. So V over delta is the total space of my degeneration. Delta is a disk. The general fiber, I'll call V. This is Calabi-Yau. Its dimension N. I'll call the central fiber is going to be called V naught. I'll assume for the moment that this is a Turin degeneration. So this is a union of x1 and x2 glued along z. So xi a quasi-Fano. And z living inside those things, xi is a smooth Calabi-Yau anti-canonical divisor. Okay, so this is one side of the picture, right? I've got this kind of these degenerations. I've got a smooth Calabi-Yau. It's breaking up into a pair of pieces. These things are glued along a smooth anti-canonical divisor. If you know about K3 surfaces, think of like type 2 degenerations. If you have a K3 surface, it comes along, splits up into. In general, there can be more than two pieces, but the kind of, the sort of standard case you have in your mind is two pieces. Okay. What should be, so the idea is what should be the mirror to this picture? Well, V is a Calabi-Yau manifold. So mirror to a Calabi-Yau is going to be another Calabi-Yau. So we'll call this thing W. And x1 and x2, each of these is a quasi-Fano. We think of this as some sort of weakening of the Fano condition. We think of Fanos. What's the mirror to a Fano? The mirror to a Fano is generally like a Landau-Ginzburg model. So one way of thinking about Landau-Ginzburg models is as fibrations over the affine line. Because we're going to quasi-Fanos, we're going to need something a bit weaker than that. So what I'm going to do is I'm going to look at fibrations over disks. So we'll take W will split into a kind of a pair of pieces. I'll call these pieces Y1 and Y2. I need to zoom up a little bit here. I'll have a fibration from W to P1. This P1 will split into a pair of pieces, delta 1 and delta 2. These will be some sort of complex disks, open or closed. From a notational standpoint, in here, I'll have a general fiber F. And that general fiber, so these, we think of taking our base is P1, topologically that's a sphere. We think of kind of, taking some sort of strip around the equator, and we take off the top and we take off the bottom, and those two pieces are sort of glued along the strip. So in each of these pieces, I can choose a general fiber. I can choose a smooth fiber in W that appears in both of these pieces. So this is kind of the mirror picture. Let me write down what all this notation means. So pi from W to P1 is a fibration from a Calabi-Yau n-fold W to P1. We think of W as mirror to V. So from this picture before, my W is now mirror to the V I had. My general fiber F let's say F is a general fiber. It's a Calabi-Yau n-1 fold. And we think this should be mirror to Z. So this comes back to the idea, if you've got Landau-Ginzburg models, the general fiber of your Landau-Ginzburg model should be mirror to a smooth anti-canonical divisor in your quasi-Fano. Let me try and shuffle my paper around so I can keep that on screen. We'll continue with the setup. Let's get a fresh bit. Okay. So what are we saying? We're saying P1 splits. P1 is delta 1 union delta 2 into two disks. And I can restrict pi yi, which is W restricted to delta I. This maps to delta I. These we think of as Landau-Ginzburg models of these quasi-Farnows xi. So we think of these pi i's we think of as being like the superpotential. Now, what do I mean by Landau-Ginzburg models for xi? I mean, these things are not Farnows, right? These things are, I mean, you could sort of think of them as being Farnows where we've blown up a bunch of points on an anticanonical divisor. So the anticanonical divisor is not ample anymore, but it still contains smooth elements. Precise definitions here are a bit hard to come by. If one looks at work of Katsakov, Kontsevich, Pantev, there's a paper by them in I think 2014. Andrew Harder did some work on this in his thesis. So what we sort of think of here is we sort of think of at least a consequence of this should be that, and I've slightly mixed my notation. Is that right? No, this should be H1, not HI. Should be trivial. And moreover, the important condition, this is the one that makes the mirror. If I take the relative cohomology of YK with respect to a fiber F, this should be equal to the sum over J down the columns of the Hodge numbers of the mirror quasi-Farnow. So the correct indices are this. So basically I'm saying, I mean, this is very much sort of Hodge number mirror symmetry, right? I'm saying the cohomology of this thing, we're talking about, very much open objects, they're open complex manifolds. So we're going to take some relative cohomology, and this is supposed to be mirror to the sum of the cohomology going, the sum of the Hodge numbers going down the columns in the Hodge theory of the quasi-Farnows. Okay, that's the kind of sort of outline of the philosophy, and I'll refer back to that as we go along. What's the sort of aim of this project, at least right now? The aim is that degenerations, and especially Turin degenerations, are quite well understood. So if we think about degenerations, there's a lot of tools out there, right? There's a lot of tools for studying how things degenerate, what the pieces look like, how the topology of the total space is related to the topology of the pieces. If you go the other way, there's a lot of tools for saying, well, okay, if I've got something that looks like a degenerate Calabi-Yau manifold, there's results on, under what situations can I take that and smooth it back out into a smooth Calabi-Yau manifold? All of these kinds of nice results we have for studying degenerations. On the other side, I mean, we don't even necessarily have a completely clear description of what a Landau-Ginzburg model of a quasi-Farnow is. Actually, I should probably note that like this definition of an LG model, if I take, obviously Farnow is a special case of quasi-Farnow. And so how do I reconcile this with my definition of a Landau-Ginzburg model of just a standard Farnow? Well, I can think of my Landau-Ginzburg model as a standard Farnow as a fibration over A1. And so all I imagine doing is just shrinking the base. So I take some appropriate disk in that A1, which contains any special singular fibers that might be living in there, and just sort of throw away the rest, right? So, by doing this, by not specifying that it works over the whole of A1, I avoid problems of, does it have a 1-point completion to P1? Because in general, if you try and do this for quasi-Farnows, you find the problem is that it predicts impossible fiber types at infinity. So, but if you restrict to a disk, then you can say, well, outside that disk, I could maybe have a whole bunch of extra fibers, much more stuff. Okay, sorry, that was a bit of an aside. Anyway, Turin degenerations in general are quite well understood. Conversely, so the idea is, can we mirror some of these results? To better understand how things work on the other side. So can I take some of my results I have for degenerations? Can I try to find mirrors for those statements which will enable me to study fibrations? Okay. So what I'm going to focus on today is a special case of this. And the special case I'm going to look at, because this is what I've been thinking about, is let's think about topology in exact sequences. Why might I care about this? I mean, you know, the first thing we think about in mirror symmetry, the first thing we learn about when we study mirror symmetry is, you know, we learn about Calabi-Yau manifolds, Hodge number mirror symmetry, right? You know, we all know the picture. So in our original picture, we've got two Calabi-Yau manifolds which are mirrored to each other. We've got this V and this W. We expect some sort of Hodge number mirror symmetry between them. You know, all of this is kind of topological statements. So the question is, you know, can we relate those standard topological invariants and the mirror symmetry for V and W to topological invariants for X1, X2, topological invariants for these Landau-Ginzburg models? So on the degeneration side, so I'm going to present a few exact sequences here. So on the degeneration side, I've got my degeneration V, and related to this, I have, I can't spell at all. I have Steenbrink's exact sequence. Steenbrink exact sequence. What does it say? It says it relates the topology of the central fiber, HKV naught. I have the specialization map. That takes me to the topology of the general fiber. How does that work? Well, by retraction, this thing is isomorphic to the cohomology of the total space of the degeneration. And so I say I go total space of the degeneration, and then I just pull that back by the inclusion to the general fiber. This then maps to HK of V phi F. What's this? This is the perverse sheaf. Perverse sheaf of vanishing cycles. If you don't know what that is, don't worry about it. I'm not going to use it at all. And then, of course, this goes up to HK plus 1 of V0. Okay, so, you know, under our picture, we should be able to, you know, if our idea about these things being mirror is correct, we should be able to find some kind of, you know, this is an exact sequence. It relates the topology of the general fiber to the topology of the central fiber. We should be able to mirror this and get some information, you know, about the on the mirror side, right? Okay, so how can we figure this out? Well, I've got HKV naught here. This is the cohomology of V naught. Oh, sorry, of V, I should say. We know what the mirror to V is supposed to be under our picture. So we know the cohomology of V. Well, under mirror symmetry, that's supposed to go to the cohomology of W. Sort of appropriately interpreted, right? I mean, you know, there's twisting of the Hodge numbers, but, you know, information about the cohomology of V is going to be mirror to information about the cohomology of W. We're being deliberately vague here. Now, the question is, what about V naught? This is the philosophy section still. Cohomology of V naught. So what should I do with the mirror here? This is a slightly rhetorical question. So the first question, I mean, you know, we start thinking about this and we think, well, okay, you know, cohomology of V naught. The first question we might ask ourselves is like, well, how do we compute the cohomology of V naught? Well, there's a spectral sequence. I think this is due to Deligne. And what does it say? It's a spectral sequence. It has E1 page equal to the following. HQ V naught P. I'll tell you what this thing is. Everything's with Q coefficients, by the way. I didn't say that. So what's this thing? This is the codimension P stratum. So in my Turin degeneration case, V0, naught, the codimension 0 stratum, this is just the disjoint union of x0 and x1. So I just treat these two things as two completely disjoint objects, direct sum over cohomology. And if I take V01, this is just the intersection between these things. X0 intersect x1. Okay. Deligne tells us this spectral sequence degenerates at the E2 term, and it converges to HP plus Q of V0. Okay, now this is something that we can think about in the mirror too, right? I mean, we've got these situation. Well, I mean, what's the cohomology of V0 naught? The cohomology of V0 naught is just the direct sum of the cohomology of x0 and the cohomology of x1. If I roll my page back up, these things appeared over here, right? This sort of cohomology appeared in this. I mean, okay, it's Hodge numbers, but this cohomology appeared in this kind of expression. So we can, I mean, the idea is like we do have some idea of how to mirror this thing. And what do we think of the mirror as being? Well, let's try and write down something that seems sensible to have as a mirror. I'm going to take some sort of intersection. That should be a Y. I'm going to take some sort of spectral sequence. So, you know, my Deligne spectral sequence is working. It's taking, you know, the E1PQ page is the Qth cohomology of the Pth codimension stratum. So in this case, I'm going to take the Qth cohomology of like the Pth fold intersection of my various Landau-Ginzburg pieces. So in the Turin degeneration case, this is very simple. So I can take this thing. Oh, sorry. No, I don't want to take this thing. Where am I getting this from, right? I'm saying, well, okay, I've got some of these sorts of things on one side, so I'm mirroring across to these relative cohomology groups. So I want to take a relative cohomology group there, coefficients in Q. Okay, what is this thing? Well, we all recognize what this spectral sequence is. This is the check to derive functor spectral sequence. Or if we're in the Turin degeneration case, an easier way of thinking about it, because the Turin degeneration case we've only got two pieces, right? So this is a spectral sequence. If you've only got two pieces, this is just relative Mayer-Vittoris. Relative Mayer-Vittoris. Okay, we know what this thing converges to. It's a standard, well-known thing. This converges to HP plus Q WF. Okay, so going back to our sort of philosophy, what do we expect? We expect the cohomology of V0 to be somehow mirror to the cohomology of the relative cohomology of W with respect to F. Everything is hand wavy right now. None of these are concrete statements. We're talking philosophy. Concrete statements are coming. Hopefully I've, you know, reasonably justified why that's a sensible thing to perhaps expect might be true. If I go back to my Steenbrink exact sequence, I've got it up here. I can do fancy things with more than one sheet of paper here. If I go back to my Steenbrink exact sequence and I go back to what I was just saying, well, I can try and start mirroring this now, right? So we sort of reckon that this thing is going to be mirror to something like HKWF in some sense or another. I'm not worrying about the degrees. We expect the cohomology of V to be mirror to the cohomology of W. So let's throw in the cohomology of W there. Do we know any well-known exact sequences that contain a map that looks like this? Well, exactly, yes, we do. I can complete this to an exact sequence like so. I can just throw in an F here, and I can keep going. So this is just the exact sequence of a pair. So somehow, you know, my claim, which I've given very, very weak justification for right now, is that these two exact sequences are in some sense mirror to one another. I'm going to note for future reference that this thing is isomorphic to the compactly supported cohomology of W remove F. So that's another way of thinking about it. That's going to be useful to us later. Okay. Halfway, are there any questions? I haven't said anything concrete yet. There's more hand waving to come, don't worry. There's more hand waving to come. Okay. So let's go back to degenerations. Let's think about things we know about degenerations. Another sequence that we have for degenerations is the Wang sequence. So what does the Wang sequence say for us? It says, I've got to get this right. If I imagine taking, so I take my degeneration, my total space of my degeneration V, I chop out the central fiber. So I've then got, you know, I can then retract that onto the boundary. So I can think of this as being a fibration over, so we can think of as fibration over an S1 with fiber V. So somehow this is, you know, we think of this as being some sort of fibration around a loop. I can take this to the cohomology of a general fiber V. Then I can apply monodromy. So this is the logarithm of monodromy. Logarithm of monodromy. And this goes to hk plus 1, V less V naught, and so on. Okay, another well-known exact sequence. This one now telling me about, I mean, really, you know, what's this one giving us information about? This one is giving us information about, you know, the action of monodromy on the general fiber, right? We go monodromy round. This is the map appearing here. This tells us we can extend this out to an exact sequence, and we can use this to study the monodromy. Okay, now, if we sort of go back to, our classic mirror symmetry, you know, we can look in Cox and Katz and various other places. You know, you look back and we say, well, okay, you know, monodromy on cohomology, you know, this can be thought of as some sort of something going on complex moduli, right? So we're doing some sort of loop around a boundary in complex moduli, monodromy around that loop. What should that be mirror to on the other side? Well, okay, we go to the other side. We're then in some sort of picture in the Kähler cone. What does this kind of monodromy around a loop do over there? Classic mirror symmetry tells us this is mirror to cup product. So this thing, this map, this we expect to be mirror to the following. So of course, HKV, you know, cohomology of V mirror to cohomology of W. And now I'm doing the cup product with a fiber in this map. So this is going to HK plus 2 of W. Of course, you know, the monodromy is taking me, if I think of the Hodge diamond of V, the monodromy is taking me across the rows of the Hodge diamond. So I expect the mirror to that to be taking me down the columns. So this is what this cup product is doing. It's taking me vertically downwards. Okay, now there's something kind of nice here. Well, okay, we'll come to that. Okay, so, you know, again, we sort of then say, well, okay, we expect we want to find a mirror to this exact sequence. this exact sequence contains this logarithm of monodromy. We want the mirror to contain the cut product. Which exact sequences do we know that contain a cut product in them? Well, I actually asked this question to Helge Rudau. I said, do you know any exact sequences that contain a cut product in them? And he said, well, I only know one, and the one I know is the Geissin sequence. So what does the Geissin sequence say? The Geissin sequence says the following. HK of W. And I have to tell you what some of the things are. So here is my cut product. I have to tell you what phi is and what E is. Phi from E to W. So this is something fibered over W. This is an S1 bundle associated to the line bundle OW of F. So what I do is I take the line bundle OW of F over W. I take just the unit circle in each fiber. That gives me an S1 bundle. I call that S1 bundle E. Phi is the map, which is mapping E to W. Now, this is very, this looks nice, right? If we look at this picture, what have we got up here? Well, we've got our logarithm of monodromy. This is mapping me from cohomology of V to cohomology of V. I've got a map here which is going from cohomology of W to cohomology of W. It's doing the right thing with the degrees, right? This one is mapping me across the Hodge diamond. This one is mapping me down the Hodge diamond. What's this kind of crazy looking object here? Well, it's a fibration over S1. I mean, so if V is a Calabi-Yau threefold, that's a real sixfold. So this thing then is a fibration over V. So this thing is some kind of real dimension 7 object, right? Over here, what have I got? Well, I've got an S1 bundle over a Calabi-Yau manifold of the same dimension. So this thing is also some kind of real 7-fold if I'm in the three-dimensional case, if I'm in the complex three-dimensional case. So this kind of, it looks like we might be on the right track because I've got a fibration over S1 with fiber V. And that somehow looks like it's being mirrored to an S1 bundle over the mirror W. Okay. Now let's start getting a bit more concrete. So, I've given you 2 exact sequences here, and I've given you some sort of very vague hand-waving justification as to why we should think of these as being mirror to two other exact sequences that you already know. Now, where this gets kind of interesting is I can interlace the Steenbrink sequence and the Wang sequence, and this is a little bit delicate to draw, so I have to pay attention here. So I'll start with Steenbrink. And this one goes down. And this one goes down. And this one goes across. So that's my Steenbrink sequence. Let me shovel it across so you can read. Now I have a map here. Here's my map N. This is now my Wang sequence. HK plus 1, V less V naught. And I can go back. HK, V less V naught. And I can go back. HK minus 1 of V. And I can go back. So I have this kind of interlacing, very well-known theorem, local invariant cycles theorem. Local invariant cycles theorem tells me, and actually there should probably be, well, I'll chop that off there. Local invariant cycles theorem tells me that this combination here is actually exact. So, the specialization map composed with the monodromy map, that's actually exact. And using that and a bunch of diagram chasing, we can actually complete this diagram. So I'm going to add a couple of dotted arrows here. What goes in here? This is the cohomology of V of my total space of my degeneration with support in V naught. And we have a couple of maps going in here. I'm not going to define what these maps are. H plus 2, V naught V, and so on. What do we sort of observe here? Well, one thing to observe here is that these two terms are Poincare dual to each other. So there's a Poincare duality map between those two. Well, there is a Poincare duality between those two. And this is very well known. What are the top and bottom rows of this diagram? The top and bottom rows of this diagram are just the Clemens-Schmidt exact sequence. So top and bottom are the Clemens-Schmidt sequence. Now, the Clemens-Schmidt exact sequence is nice and it's not nice, right? I mean, it's nice for one. The reason that it's nice is because all of the objects in here are very, very nice and computable things, right? I don't have any strange real manifolds of odd dimension, right? I mean, all of these things are nice complex manifolds. I'm not dealing with some weird sevenfold fibered over S1. I don't have any perverse sheaves of vanishing cycles. I've just got cohomology of a central fiber. That's a nice computable object. I've got cohomology of my general fiber. This thing is Poincare dual to that thing. This is a great tool for doing computations, right? The reason it's not very nice is it's a 4-term exact sequence rather than being a 3-term exact sequence, which means we have to be careful with it. And there's also like an odd and an even version. The shift in degrees here goes from k to k plus 2 rather than what we usually expect, k to k plus 1. But anyway, as a tool, it's very nice. Okay. Everybody happy. As happy as you can be, given I've not said anything. Right, so now we get to the meat. The question is, can we do the same thing on the other side? So I'm actually going to slightly, this so far has all been nice motivation, and I've been assuming things like collabialness. I'm actually going to relax my assumptions quite significantly here. The notation will still say the same, but I'm just going to let pi from W to B be a projective fibration. From a complex n-fold, W, to a complex curve B. Then here is the theorem. The top and bottom rows in the diagram below okay, what's this diagram going to be? So in my picture up here, I have my Steenbrink sequence going like this. I've claimed that my Steenbrink sequence is mirror to the exact sequence of a pair, which I'm going to write in this way. I'm going to use compactly supported cohomology because it's going to make more sense for this. It goes to HKW, goes to HKF, goes to HK plus 1, compactly supported, W less F, goes to HK plus 1, W. Whoops. So that's my exact sequence of a pair. Moreover, I am kind of hoping that the the Wang sequence is going to be dual. It's going to be mirror to the Geisen sequence, and I can put that one in here. So this is cut product with F cut blank. This is going to HK plus 2 of W. That's going up to hk plus 2 of E. And that's going back down to hk plus 1 of W. So very happily, I mean, you know, like the groups that I'm getting here match up, right? I mean, you know, I get an hk plus 1 of W in both cases. That'd be worrying if that didn't happen. Hk plus 1 of E goes down to hk plus 1 of W. Okay, so we have this far. Now, I haven't told you what goes in these extra spots, but what we do know is that on the Clement-Schmidt side, these two objects are Poincare dual to each other. So if these two things are Poincare dual to each other, what does that, what do we expect here? Well, we expect Poincare dual of this thing. That's easy enough. That is one way of thinking about it, is just taking away the compact support. That gives us this thing. I'll tell you what these two maps are in a second. hk plus 2 of W less F. And so it goes on. So this map here, this is just the pullback of by the inclusion. So I can just include W less F into W. I can just pull back by that map. This map is the slightly more complicated one. This is the composition. So I've got, there is a boundary map from here to this. There's a natural exact sequence with those in them, and then I can compose that again. My paper's not quite wide enough. I didn't think this through. HK plus 1, compactly supported, W less F. So, I mean, another way of thinking about this, and this sort of mirrors where the map comes from in Clement-Schmidt. You know, I could also think about this as a homology group. Compactly supported cohomology is Poincare dual, is you know, can be identified with homology. So I can think of this as being a boundary map from cohomology and then a boundary map from homology composed together. Okay, so I have this picture. So the claim is, or the theorem is, these are exact if and only if the following condition holds for every 0 less than or equal to k less than or equal to n minus 1. Remember, n minus 1 is the dimension of my fiber. The Hodge-Riemann bilinear form, which I will remind you is defined in the following way. Qk of alpha beta is minus 1 to the power of a half k minus 1 times the integral over f alpha wedge beta wedge. The pullback of 8, I'll tell you what I is in a second. I'll tell you what that is in a second. So I assume my fibration is projective. So H is a relative ample class. I can't spell. H is a relative ample class on W, and I is the inclusion from F into W. So I'm taking the relative ample class on W, I'm pulling it back. I'm pulling it back to F, and then I'm using that to define my Hodge-Riemann bilinear form. So this is a bilinear form on the kth cohomology of F. And what I want is I want this to be, I know it's always non-degenerate, that's an easy thing, but I want it to be non-degenerate on the image of I upper star sitting inside HK of F. Okay. This is a rather sort of strange technical condition, but I sort of want to convince you that in some cases we care about, this is actually a completely sensible thing. I don't know about the absolutely general case, and I also sort of, yeah, we'll sort of discuss. So anyway, I mean, you know, the upshot is we have this diagram, everything is exact, everything commutes. It's quite nice as long as we have this sort of technical condition on the Hodge-Riemann bilinear form. So let's have a look at that condition a little bit. Remark. If W is an elliptically fibered K3, this condition always holds. So if we're in the situation where we have a where we have some sort of situation where we've got a fibration of a K3 surface over a over P1, by elliptic curves, this thing always holds. That's actually pretty trivial. There's not an awful lot to check there, largely because a lot of the cohomology just vanishes. Slightly more interestingly, if W is a K3 fibered Calabi-Yau, this condition is equivalent to the image of this pullback. So if I take the pullback of if I take the pullback of classes from W and I intersect that with H2 of Fz, remember everything for these exact sequences over Q. If I intersect that with H2 of Fz, I want that to define a lattice polarization. On F. So this is a sort of very sensible thing, right? If I want to talk about mirror symmetry for instance, F with Z, then I need some sense of lattice polarization on my F, so that I can do, you know, Dolgorchev-Nikulin style mirror symmetry. So where does that lattice polarization comes from? This tells me this comes from, I take classes in, I take classes in H2 of W, I pull them back onto H2 of F, I intersect those with the Z cohomology, that should give me a lattice polarization, and then everything works. The sort of interesting case, and why, I haven't had as much time to investigate these conditions I'd like, and I'm not entirely certain that it's not sort of always true in the cases that we might care about. But sort of food for thought here, I guess, is if W is a Calabi-Yau fourfold, then my Hodge-Riemann bilinear form Q3, which is going to be the one on the third cohomology, this is going to be skew symmetric. And that then means, this is, it's no longer completely obvious to me, if we're effectively what happens here. So if we're in the elliptically fibered case, there's not enough cohomology for this to be an interesting condition. If we're in the K3 fibered Calabi-Yau 3 case, this thing actually broadly ends up working out fine. And the reason it ends up working out fine is we're working in H2, and we sort of know we've got enough stuff to make this non-degenerate because we've got the pullback of the ample class. The ample class is living in H2. We know we've got enough stuff in there to make this thing non-degenerate, right? We've got an ample class sitting, we've got a relatively ample class, I should say, sitting in there, and that relatively ample class has got to intersect everything. So this thing is not going to be degenerate. So the interesting case is when we go up to Calabi-Yau fourfolds, then we have a situation where, okay, now we're working in H3. We don't have like the nice ample class sitting in there. We don't even have powers of the nice ample class sitting in there, right? And what's more, it's skew symmetric. So if we start pulling classes back in, we're going to get things with self-intersection 0. So it doesn't seem obvious to me, like non-degeneracy doesn't seem quite so obvious in this setting. So that's something which I admit requires more investigation, and I haven't got around to yet. Okay, so what have I done here? I mean, I've sort of presented some sort of very weird exact sequence. And everything along here is calculable, but it's not giving us an awful lot of information, right? It's just saying, some topology. You know, what we'd really like, if we want to do mirror symmetry, we'd really like information about things like Hodge numbers, right? Also, something to note in here is that, you know, somehow all the structure of my degenerations, everything that I knew about, you know, my Turin degeneration is splitting up into pieces, and, you know, the splitting of the base, all of that is gone, right? There's nothing here. All I've got is cohomology of W and cohomology of W with a fiber chopped out, right? I mean, like, what's the deal? Why should I care? There's you know, there's sort of probably a reason why I haven't been able to find this in the literature anywhere, and the reason is it doesn't seem terribly interesting. The reason is, well, I mean, you know, you look back at your Clement-Schmidt exact sequence. Your Clement-Schmidt exact sequence doesn't look all that interesting either, right? I mean, all it's doing is saying, here's the cohomology of the central fiber, here's the cohomology of the general fiber. You know, mix these two things together. Where it gets interesting is the Clement-Schmidt sequence is a sequence of mixed Hodge structures. And we've got weight filtrations on there, and we've got Hodge filtrations on there, and those encode actual interesting information about, you know, what is the central fiber? What is this action of monodromy doing? So the general idea here, which I have strong evidence for, but haven't been able to prove well, I've been able to prove in special cases, but haven't been able to prove in generality, is that we can actually put something like mixed Hodge structures on these things, which should be mirror to the mixed Hodge structures in the Clement-Schmidt case. So I'm going to sort of state this as a slightly vague conjecture, and this is not a conjecture. This is not the sort of conjecture that you should all rush home and try and prove, because I'm fairly confident that when I'm not spending all of my time trying to figure out how to deliver my lectures online, I could probably tie this up fairly quickly. Just haven't had time to get round to it yet. So I'll just sort of talk about the weight filtrations. There are weight filtrations on the terms of this exact sequence. That are respected by the sequence. Okay, I mean, I can't make a statement that vague without giving you some information. So what do we expect? Well, really, I mean, you know, okay, let's look back at this sequence a little bit. So I should tell you what are the weight filtrations on here. I mean, this is just cohomology shifted up in degree by 2. So it's going to be the same thing on this. So the weight filtration on the cohomology of W is given by, and, you know, I'm brushing some things under the rug here because, you know, really we probably have to talk about some sort of sum over cohomology groups rather than individual cohomology groups, but it'll be fine. This is given by the weight filtration coming from a nilpotent endomorphism. I can't spell nilpotent. So this is exactly the same as in the Clement-Schmidt case, right? Where do we get the weight filtration on the limiting mixed Hodge structure? The weight filtration on the limiting mixed Hodge structure comes from, we look at the monodromy. The monodromy is a nilpotent endomorphism that gives us a weight filtration. So we just do exactly the same thing here. Cut product with F. F is a fiber. That's a nilpotent endomorphism, right? We cut product with the fiber twice, the fiber disappears. The interesting one is, well, where do we get the weight filtration on here from? I mean, again, mirror symmetry is giving us a clue. Where did we get the weight filtration on the mirror thing? The mirror thing was the cohomology of the central fiber. Where did we get the weight filtration on that from? It came from the Deligne spectral sequence. We know what we think the Deligne spectral sequence should be mirror to. So the weight filtration on this thing, which I'll remind you is isomorphic to this. This is given by the check to derive functor spectral sequence. Oh, where am I? Oh no, I'm okay. I'm up here. I sort of lost where my camera was pointing there. Check to derive functor spectral sequence. Okay, finally, I've got one more to tell you about. Where's my pen? Where do I get the weight filtration on this thing? Well, again, if I take my inspiration from Clement Schmidt, this thing is Poincare dual to that thing. So the weight filtration on here is just the dual to the weight filtration on there. So the weight filtration on HK W less F comes from Poincare duality. Because this thing is isomorphic to HKC W less F dual, right? Okay, so this is still a conjecture, not because I think it's particularly hard, but because I haven't had time to do it. But this has been verified explicitly for the setup I mentioned at the start. So let's say Turin degenerations of K3 and Calabi-Yau 3. But I mean, sort of philosophically, this should be true in much more generality. Now, just to sort of wrap up here, I mean, okay, something to say here first is once we get into this situation, here is where our Landau-Ginzburg models are hiding, right? This spectral sequence is relating the topology of our Landau-Ginzburg models to the topology of this total space. So this weight filtration is where the topology of these Landau-Ginzburg models are hiding. So just as in the Clement Schmidt case, the topology of the pieces of our degeneration, the topology of our Farnovs, is all wrapped up in this Deligne spectral sequence. That's where it's all encoded. Over on the other side, this is all going to be encoded in here. So by putting these weight filtrations on, we're able to extract back out the information about that cohomology, and we're able to explicitly link that from this split situation. You can relate somehow the cohomology of this gluing across to the cohomology of the total space. So it's doing the same kind of thing for us. Now, of course, going back to the philosophy here, everything I've said is to some extent for Turin degenerations, but Turin degenerations are far from the only type of degenerations we can have, right? So we could say, well, okay, if we've got a Calabi-Yau threefold, we could split it up into, some sort of chain of Calabi-Yau threes. We could also split it up more severely into, pieces which are glued sort of in, some sort of football-like configuration, right? Some sort of type 3 degeneration. Now, from this picture, it's kind of clear what should be mirror to that, right? And the mirror should be, well, okay, now instead of having a fibration over a one-dimensional base, we have a fibration over a higher dimensional base. Rather than splitting this up into two pieces, we split it up into a number of pieces which correspond to each of the bits of each of the bits of our splitting, right? So we each of the bits of our degeneration, we break our fibration up into a whole load of chunks, and then the Clement Schmidt sequence is saying, well, okay, here is how that degeneration, the cohomology, the Hodge theory of that is related to the Hodge theory of our general fiber. On the other side, there should be, a similar picture along these kinds of lines, which is saying, because, where did I put it? Too many bits of paper. Nothing in this set of sequences here is saying anything at all about the way I'm splitting this fibration up, right? So the details of the splitting of the fibration are all buried in the weight filtration on this thing, and that weight filtration is just the check to derive functor coming from the check to derive functor spectral sequence. Check to derive functor spectral sequence, well, that doesn't matter how you break your stuff up, right? I mean, this is just saying, you know, if you take your pieces, your sort of your open charts, it's saying this is how you build the cohomology of the total thing out of the open charts. The fact I've only got 2 here is just a simplifying assumption. I mean, there's really no reason why you can't try and do this for more and more bits. So that's some direction that this potentially goes into. The interesting part of that story is not so much sort of the philosophy of where this should go, but somehow what the mirror to F should be. Because if we haven't, you know, this cup product, if we're in the type 3 degeneration case, the cup product should have, you know, it should be nilpotent of order 3. And so just taking a fiber of the fibration is not going to work, because if I, you know, once I do cup product with a fiber twice, then it dies. So I'm going to need to take something a bit bigger than a fiber, right? Perhaps a fiber over a carefully chosen divisor in the base, or a fiber over some kind of skeleton of the splitting. Anyway, that's a kind of hand-waving picture, and I'm 2 minutes past, so thanks for your attention.
All right, thank you, Alan. I'm going to ask everyone to unmute to applaud.
Thank you.
Okay, so now we should probably all mute unless we have a question. Any questions for Alan?
I have a question for Alan.
Hello, Lawrence. Okay. I haven't seen you for a while. How are you?
I'm good.
Where are you now? You went to...
Everyone asks me this question. I'm in Boston.
Oh, okay. Cool.
Right now. But I'm trying to work out how not to be in Boston. But,
okay. Because last time I saw you, you were off to...
Taipei.
Taipei, that's the one, yes.
No, yes, I'm in Boston College with Chile. Right, so sorry, to ask you something which I guess Chuck knows that I've been annoyed about for some time. If I degenerated to, rather than just a simple Turin splitting where I have 2 pieces, if I had a chain of pieces in the middle, what should be the mirror condition to this? I think it's implicit in what you said. But...
So it should be, and the details of this are not yet worked out either, but it should be a slicing. So you imagine, if I still have my bit of paper here, so you imagine, I mean, it's the same picture where you have V and you have W, and W is fibered over P1. And this time now, this thing looks like some kind of chain. And over here, what we now do is we take our P1, which is topologically a sphere, we cut a cap off the top, we cut a cap off the bottom, and then we slice the middle bit.
Mm-hmm.
And so, I mean, this is sort of interesting because one can write down nice examples for K3 surfaces where this works like absolutely beautifully, right? You know, you can see, okay, you know, I have a type 2 degeneration of K3 surfaces that's got some middle components. I can look at the, you know, what happens to the lattice polarization when I try and, you know, degenerate out and restrict to this thing. And then over here, you can say, well, okay, you know, I've got some sort of special fiber in my elliptic fibration living over the top, and some sort of special fiber in my elliptic fibration living over the bottom. But I've got some other ones as well, and those other ones should be thought of as sort of living over here. And so somehow it's you know, how the lattice polarization breaks up on this side corresponds to some extent to how the fibration breaks up on this side, because the end caps here are just the same, right? These are rational surfaces. They're still quasi-Farnows. The interesting thing is the middle things are not quasi-Farnows. And so then the question is, you know, well, there's a lot of questions here, and one of them is, you know, what should the sort of mirror Landau-Ginzburg model be? our hypothesis, which is based on very little aside from this sort of vague philosophy, is it should be a fibration over an annulus.
Should be like a GM, fibration
Yeah.
over GM.
Yeah. So, or you know, I mean, even better, like a fibration over, sort of like a fibration over S1, right? So you've sort of got, you know, some sort of, you know, you think of these as like elliptic fibrations or some sort of, you know, K3 fibrations or something like that. And the challenge with the reason that I restricted, and I hinted at this at the end, the reason I restricted to these Turin degenerations is the real challenge here is, you know, currently to make this work, when I split up into two pieces, I can split up into two pieces. I can assume there's kind of a little bit of an overlap between the two. And then to make everything work, I can pick my fiber with which I'm taking relative cohomology, and I can pick that to live there. So there's my fiber F. And the problem is, if I want to try and do this picture in this situation, I then need to know, like, what's my fiber F? And one starts to get kind of difficulties with, like, you know, these spectral sequences that compute the relative cohomologies. You know, I sort of need to have the same, they need to sort of be relative to the same thing. So that's the obstacle in this case is, or well, the obstacle in all the generalizations is really like, what is the correct analog of this? You know, so for your Landau-Gisborne models, when you're doing this mirror picture, where's my bit of paper that's got this on? This one. You know, so we have this nice kind of formula, right? And the question is, if we're in a more general situation, so where we don't have a quasi-Fano, so where we have one of these maybe sort of central pieces in a type 2 degeneration, or we have a type 3 degeneration where this is maybe going to be, you know, some kind of quasi-Fano with some sort of cycle of anti-canonical things on it, so it glues onto other pieces to make a type 3. Like what's the correct analog of this, and in particular, what do we put on the left-hand side here?
Sure. So sorry. So just to, can you go back to the previous page?
Yeah, it's here somewhere. That one.
This thing which you've sliced is also itself still sort of fibered over P1.
Well, this is the P1. This thing I've I'm slicing the P1, and so the fibration is just the restriction to each of the slices.
Okay, that's a pretty picture.
And it sort of works nicely, right? Because I mean, you know, somehow what the ends are doing should be the same. So, you know, what the ends are doing here is exactly the same. I've still just got fibrations over disks for the ends. The difference is I'm bunging some stuff in the middle.
And then some singularity theory into the middle as well.
Yeah, it's basically, I mean, you know, because you can also, I mean, there's a lot of stuff you can do here, because you can think of, well, okay, you know, if I've got, you know, I can have some sort of Turin degeneration consisting of two pieces, and I could maybe do some base change so that it picks up some extra components. And then I could do some kind of like flips or elementary transformations to move some divisors from the ends into the middle. Yeah. And somehow, what does that correspond to here? Well, we sort of add in an empty annulus, and then to do the flips corresponds to sort of moving pieces of the bad fibers here. You know, you sort of you sort of pull a nodal thing. You know, if you think about K3 surfaces, you know, you take some degenerate elliptic curve, and out of it you can pull a sort of I1, right? A nodal elliptic curve. And then you kind of shuffle that along, and it just crosses over the boundary and ends up in here.
Yeah.
And so that's kind of the opposite to like a flip operation.
Sure. Okay. Translating this into this gross Siebert setup is a pain, but
I think I mean, you know, like I think that I keep coming across things that remind me of things I know from gross Siebert. So I think that there's some, you know, I mean, so somehow I feel like, you know, in gross Siebert you have these, you know, you come into these toric degenerations, right? And a lot of the stuff, a lot of the data there is encoded by sort of encoded by these sort of tropical skeleta, right? And I sort of think that if one were to take this and say, okay, now let's take a maximally unipotent degeneration here. We have some maximally unipotent degeneration here. This thing on this side corresponds to, well, okay, we sort of, we then have a fibration. To some extent, we have a fibration of something over itself. So this splitting just corresponds to a splitting of our object. That's to some extent our toric degeneration. Our fiber F sort of needs to be everywhere at once. So that kind of feels a bit like the gross Siebert skeleton, right? Like tropical skeleton. So I think there's a link here, and I'm a long way off being able to make it explicit. But there's things I see and think about here, and there's things that I'm aware of from gross Siebert that look like somehow we're on the small degeneration end, right? The simple degeneration, and gross Siebert is doing this from the opposite direction of we've taken a maximal degeneration and we're doing the same thing. And there's it feels like these are on two ends of a spectrum.
Let me ask you more, but I should not take up time from other people who might have questions.
Yeah, I think Klaus has had his hand raised for a while. So maybe we'll move to Klaus and we can come back.
Yeah, sort of thinking, going in the same direction. I mean, you mentioned that there should also be a picture for type 3 degenerations. So I wondered if you take sort of one of the simple cases, you take, say, a quartic K3 surface and break it up into 4 P2s, intersecting like a tetrahedron. What would the sort of the mirror picture be there? What do you expect? Have you worked out that example?
I mean, the challenge with doing this the challenge is somehow that I have to get the numbers right, but like a type N degeneration should correspond to a fibration over an n-1 dimensional base. So doing this for K3 surfaces is sort of problematic because it predicts that if you have a type 3 degeneration, it predicts the base should be 0 dimensional. So what I think this should correspond to would be a situation where we just take the mirror K3 surface and, we consider it as a fibration over itself, which means we just have some kind of splitting of this K3 surface into pieces, and the pieces in the splitting of the K3 surface to some extent correspond to the pieces in the degeneration. And I think there's some sort of way of rephrasing this as sort of classical mirror symmetry. But anyway, I think there's sort of the interesting case here, and the one I'd like to try and get at is if I take a type 3 degeneration of Calabi-Yau threefolds, because that should then, I think, correspond to some kind of elliptic fibration over a two-dimensional base. And the LG models should, to some extent, the LG model should correspond to elliptic fibrations over patches of surfaces.
Or you could take a K3 type 3 degeneration and then take HILP2. That would be some hyperkähler degeneration.
Yeah, that's another. I mean, I've largely stuck so far to surfaces and threefolds, but yeah, I mean, there's a lot of directions to go in with this, and I'm sort of I'm hoping to. I've a lot of the stuff at the end was very speculative, and I don't have any, well, aside from some type 2 things, I don't have much in the way of concrete examples. It's just a sort of observation that there's very little of what I'm doing that doesn't seem to work in more generality. Yeah.
Thanks anyway. Thank you.
Yeah, no problem. I have more questions than answers, unfortunately, but that's always a good situation to be in, I guess.
Absolutely. Speaking of which, are there any other questions from participants?
Can I ask?
Sure, go ahead.
So are there any relation between this description and the SYZ picture? Because, for instance, in the case of the degeneration of quartic K3 surface to the union of 4P2, it's possible to construct a Lagrangian fibration on the K3 surface, starting from the Lagrangian fibration on each of the copies of the P2s, or better, of the C star times C star, and then glue it I mean, patches together all these pieces, which seems very similar to this approach.
Yeah, I mean, I think you know, the person to talk about the person to talk to about this is Atsushi Kanazawa, right? He's he's explicitly, he wrote a couple of papers about the relationship between this picture, specifically about the relationship between this and SYZ. And so I think there is a correspondence, a link there. I'm not sure I can say anything more than what you've already said.
I see.
But I mean, you know, so Atsushi has done this for. He's looked at the one-dimensional case, so where we're looking at. Yeah, he somehow looked at like compatibility of this with mirror symmetry for elliptic curves. And he's also looked at this for things like abelian surfaces and abelian varieties, where sort of SYZ is much easier, right? Because there's not, you know, you've really got just you're not sitting in a situation where you have degenerations of things. I mean, you know, I somehow suspect that the way that would come about is through some sort of Gross-Sieber-esque picture, right? Where, you know, I mean, you can to some extent recast Gross-Sieber as SYZ with appropriate degenerations allowed in various places, and yeah, I sort of suspect that it will be a picture somewhat like that.
And maybe I miss it from the conjecture. I mean, you said that there should be a weight filtration on the cohomology of W, but this should match the weight filtration on the cohomology of V.
Yeah, well, okay. I'm so what I should really be saying is I should be taking the when I say cohomology of W, I should really be taking the direct sum of the even cohomology of W and the direct sum of the odd cohomology of W.
Okay.
Because the weight so the picture here is going to be interesting because there's a lot of interacting filtrations here, and there's mirror symmetries between them, but it sort of shifts things around. So what I think is currently the case, is if you look at total cohomology, so you can recast this in terms of, okay, total even cohomology. You can recast everything in terms of total even cohomology. If you think of the Clemens-Schmidt exact sequence, you can then have three filtrations on there. So you can have the weight filtration, where you basically are just taking an appropriate direct sum with appropriate Tate twists to account for the degrees. So you've got a degree filtration, which is the filtration by, you know, we're taking the degree of cohomology. You have the weight filtration with appropriate Tate twists to make it compatible, and then you have the Hodge filtration. On this side, you do the same kind of thing. You do you have a degree filtration, which I've kind of swept under the carpet by when I was, you know, writing this stuff out. And I've lost my bit of paper now. There it is. When I was writing this stuff out, I put the degrees in explicitly, right? But if we take a sum, so this is everything in the top is even, everything in the bottom is odd, for instance. So we take even cohomology on the top. We have a degree filtration, we have a weight filtration, we have a Hodge filtration. The weight filtration is the interesting one because the other ones are obvious. But the mirror symmetry between the Clemens-Schmidt and this, I think, should take the degree filtration and the Hodge filtration and interchange them. So this corresponds to, you know, the fact that mirror symmetry takes, you know, the Hodge filtration going across and flips the diamond, right? So somehow, like, the weight filtration should live on, but the other two should get interchanged.
Do you know if there is any relation between the picture of Arthur Kazakov, April Jakowski, about P equal W exchange, so exchange of perverse filtration and weight filtration? Because I can see that implicitly there is some perverse filtration appearing, like the image of I star is the top graded pieces of the perverse filtration.
Yes, I strongly suspect something like this is true.
Okay.
So yeah, I mean, as I said, this is kind of the next stage in the discussion. So, and I know that I know that the Katsakov etc. school has been doing work on this stuff, so I need to. I'm trying to remember. I had a chat with Viktor Przylkowski about this last year, and I would need to go back to my notes about that. But yes, I expect there to be some relation there, and there are a lot of filtrations loitering around on here, and so I kind of yes, but I sort of expect. I expect, appropriately speaking, the one that I discussed to be the filtration which is mirror to the weight filtration on the other side.
Mm-hmm. I mean, the perverse filtration, for instance, can be expressed in terms of the cap product with the relative ample class. So
yeah. So that sounds So that sounds on So I guess on W.
Yes.
I guess that's exactly the perverse filtration.
I see.
And so I guess the difference here is that okay, there's a filtration living on this thing, which is coming from the gluing, and that the whole picture is exact.
I see.
Yeah, I guess if it's if that's the same thing, I've been calling it the the filtration from a nilpotent endomorphism, but it's
if you fiber over P1, you will have just two pieces of the filtration. So maybe that's why you have that condition on the bilinear form only. I mean, on that image, because that's. I mean,
so for Turin degenerations, this filtration is very, very simple.
Yeah.
And I would be interested to see if I'll have to look up this paper, because I'll be interested to see if do you know if they do this for fibrations where like the base is higher dimensional?
I mean, conjecturally, yes, but I mean, I don't think that a complete paper is already on the archive. I mean, the one that is on the archive is very short, and you refer to a future one.
Yeah. In traditional style. Because I guess the challenge here, as I've sort of been speculating wildly, the challenge here with generalizing this to more interesting types of fibrations and degenerations is sort of exactly what do we do with this F. And so having, what is for a higher codimension for a fibration over a higher dimensional base, what do we put in this space here? And what I think it should be is I think, we should take some kind of something constructed on the base, either, some sort of special divisor or some sort of, like tropical skeleton or something like this, which sort of has appropriate intersection properties with itself, so that when if you take this and intersect it with itself once, you then get a fiber, and if you intersect it with itself again, then you get nothing, right? So sort of.
I mean, when you define the perverse filtration, you take the kernel of the restriction map from the pullback of a general hyperplane or intersection of hyperplane, if you start with an affine base, and that's similar to what you are saying.
I sort of thought about this, but I feel like one wants to possibly take a bigger divisor than just a hyperplane, because you want to make sure that it intersects all of the sets on your kind of covering.
I see.
So if you're on your you have this splitting of the base of the fibration, and whatever you take there, you need it to intersect all of the sets. And like for a fibration over P2, it seems like maybe like a hyperplane class is the right thing to take. But then if you've got some intersection over a more general kind of a rational surface or something, a fibration over a rational surface or something, one needs some reasonable way of picking the right thing in the base to take the pullback of to be your class. So yes, I'm this is the next stage, and I'm planning to look at that stuff. So thank you for the heads up.
Thank you for the talk.
Okay, wonderful. Are there any other questions from participants? Okay, if not, let's I'll ask you to unmute, and we'll thank Alan once more.
Thank you.
Thank you all for listening. I'm sorry it wasn't more concrete.
Was good. Hi Mirko, where are you now?
I'm in Bonn.
Ah, you're in Bonn.